This is problem 19-45. A 2-pound sphere falls and bounces on a 10-pound plate that is resting on the ground. If the sphere starts from rest 6 feet above the plate and rebounds to a height of 5 feet after the impact, determine A, the coefficient of restitution for the collision, and B, the height that the same sphere would rebound if the 10-pound plate were resting on 2 springs, each having a spring coefficient of 120 pounds per foot. Okay, so they are asking us first to have a sphere that deforms and has an elastic collision with a plate just sitting on the ground and bounces back up. And so some energy is going to be lost due to the deformation. Maybe the ball makes a sound. All of these events require energy. And so that is the reason for the ball bouncing up to only 5 feet after dropping from 6 feet. Right? The deformation creates heat and things like that. That's energy lost. Right? Now, in part B, they're asking us to find out how high the ball will bounce if the plate was on some springs that would compress and then push back as well. I would imagine, based on the intuition that I built, that means that there'd be less deformation in the ball, and there would be deformation in the spring, and the spring would be a more efficient system for this. And also, our springs are ideal in this case. So I think that in this problem, based on how the math will be worked out, we are assuming that the ball is not deforming in this case, because they don't give us a height. They don't give us a value where the ball gets to a new height and loses energy. So let's just, but this is my guess. Let's do the math based on what we're taught, and let's see if we have to recalibrate our intuition. So part A will have 2 stages. First, we need to find out what kind of energy the ball has on the way down. So that way during the impact, so if this is like the ball squished on the plate, we can find out how that ball will rebound up to 5 feet. And since we know that we're going to go from 6 feet to 5 feet, some energy is lost somewhere. Right? We can use the work energy method to find out how fast the ball will be traveling at the point of impact down by the plate. So initial kinetic energy plus initial potential energy plus work equals the final kinetic energy plus the final potential energy. All right, well, what do we know? We know the ball starts up in the air at rest. So we have 0 for the initial kinetic energy. We do have some gravitational potential energy. All right, is there any work done? Well, if we're considering the potential energy due to gravity, then we don't talk about the work due to gravity. And then we have a final kinetic energy, but we do not have a final potential energy. So, because this is the instant before the impact. Technically, the impact, like the squishing of the ball, would be a potential energy that would result in the rebound. But we are talking about not actually the moment of squishing, but the moment just before squishing. And even then, that wasn't a very good picture. It should be like just in contact with the plate. Okay, so let's work with, oh, I didn't zero out my work. So let's work with the terms that we have. We'll have a 2-pound sphere, so a force of 2 pounds, a weight of 2 pounds, times 6 feet to fall. So there's our potential energy. And then that's equal to 1/2 the mass, so 2 divided by the acceleration due to gravity, times the velocity, and this is technically the initial, because we're talking about we haven't gotten even to part A. We're trying to find the initial velocity due to the impact. All right, so that's what we're solving for. And the initial velocity is equal to 19.657 feet per second. All right, now for part A, if the ball rebounds up to 5 feet, then our work energy equation changes a bit, but not by much. Basically, the kinetic energy that was going to be the final is going to become our initial. I shouldn't say it that way. Meaning that we will have an initial kinetic energy. We will not have an initial potential energy. We will still not have work. But now we will have a 0 for our final kinetic energy because the rebound will be all the way up to the top. And now we will be left with a final potential energy. So that's what I meant by the swap, is that the zeroing swaps places between the potential energies and the kinetic energies. Okay, so if we can find the final kinetic energy, then we will end up with 1/2 the mass, and then the final velocity squared, plus the 0 plus the 0 equal to the 0, plus now we'll have the potential energy, but only to 5 feet. If we solve for the final velocity, we'll get 17.944 feet per second. All right, why do we do that? Because these are the terms we need for the coefficient of restitution. So make sure you're looking at the book and look at pages 452 and 453 for more information on the coefficient of restitution. So 452 and to 453. Right, that equation is the final velocity of like the second object B, minus the final velocity of object A over the the initial velocity of object B next to, or minus the initial velocity of object A. This is also equal to the velocity of B relative to A final and over the velocity of B relative to A initial. All right, well, what do we care about? We care about getting this term. And so one way we can do that is using this form of the equation. And how do we go about that? Well, we know that we just found the final velocity of the ball, and we found the initial velocity of the ball. And we also know that the plate, A, doesn't move and doesn't move both initial and final. So there we go. We can use this equation to find the coefficient of restitution, which if we plug in E equal to 17.944 minus 0 over negative 19.657 equal to 0. Now why negative? Because the velocity is going in the opposite direction. It's going down initially and the velocity is going up in the final. Oh, by the way, I forgot my minus sign here, and look at the book. There's a minus sign in the equation as well. Now this calculates out to be 0.913. That's our coefficient of restitution. Okay. Part B asks us to find the height of the same sphere of rebound if the 10-pound plate were resting on two springs, having a spring constant of 120 pounds per foot each. So what we can do, we can take our calculated initial velocity, that doesn't change for the ball will still fall 6 feet, and we'll have a velocity of 19.657 feet per second on the way down. Now, the impact with the plate is still going to result in being 0 velocity when it is impacted, and the plate will go back up to 0 velocity again. That's why the ball will leave. And that means that the coefficient of restitution is going to be the same value. So we're still can use this number. All right, and so we can use the linear momentum equation to find our new final velocities. All right, so let me go to another page here. If we talk about the momentum of the ball, the momentum of the plate, the impulse, remember, this is a collision, So there's no external impulse forces, so 0. In other words, I'm doing this initial momentum, and then we've got the impulse. And then we also end up, and this is 0, and then we end up with the final momentum. And this is of the two objects together, because they're part of the same system. All right, well then we'll have the mass of the ball times the velocity. We know it's negative 19.657. Okay, and then I'm just going to write this just to be clear, and then the plates are going to be the mass times 0 velocity. Okay, and then plus no impulse, and then equal to, and I'll go ahead and bracket in the momentums. So now the final momentum is going to be the mass of the ball, 32.2, times the velocity final. All right, and then, and this is the ball. And then the plates are going to have a mass divided by 32.2, and they're going to have a velocity of plates final. All right, so then that means that we can take the coefficient of restitution and we can plug in the values that we found, that we already know. We know that initially we're going to end up with a 19.657. Oh, minus 0, the initial. But I misspoke. I remember that I said that the final velocity of the plate will be 0. It won't be 0, but it will be lower than what the ball is going to travel, because the ball will have uncompressed from its impact. Okay, so this allows us to have two equations, two unknowns, and we can solve for the final velocity of the ball and the final velocity of the plate. Sorry, this should be a B. And so the final velocity of the ball is equal to 11.68 upward, and the final velocity of the plate is equal to negative 6.27, and that's downward. All right, and they want us to find the height that the sphere will be. So now we can just use the work energy equation again, and we can get that the initial kinetic energy of the ball at this stage of going up is going to be 1/2 times the mass, and then times the velocity squared, and then plus no potential energy plus no work equal to no final kinetic energy, because the ball will have stopped, and then plus the weight times the height that the ball travels. Okay, that's the potential energy, gravitational potential energy. If we solve for the height, we get 2.12 feet.